So friends, a random walk basically means a variable is moving randomly without any predictability towards it. So if this has to happen in terms of timeline, it can be represented like this. xt is equal to xt minus 1 plus an unpredictable error. An unpredictable error. Okay, and this is unpredictable and random both. Basically, random, unpredictable, you can interchange the meanings of them. They mean basically the same thing. Unpredictable or random, right? So this is the equation of a random walk. Now, why am I calling this as a special case of autoregressive? So an autoregressive model looks like this. xt is equal to b0 plus b1 xt minus 1 plus error. This is an AR1 model. Now, let's make b0 is equal to 0 and b1 is equal to 1. This becomes exactly like the random walk equation. xt is equal to xt minus 1 multiplied by 1, which is the b1 plus the error. Right? So this is a case of special case of AR1 model, random walk. Here the expected value of xt is equal to xt minus 1. Right, friends? Why? Because the expected value of the error can be nothing but 0. Why? I'll tell you in a while. And the expected value of the variance is equal to sigma square. Similarly, expected value of the covariance is equal to 0. Now, because this is an autoregressive model, the required condition for an autoregressive model to be valid is that it has to be covariance stationary. So is it being covariance stationary? Let us have a look at that. The expected value of xt is equal to, the best case can be xt minus 1, because expected value of error is equal to 0. It is equally probable that the error will be equal to minus 0.1 or plus 0.1. It is equally probable it will be equal to minus 0.2 or plus 0.2. It is equally possible that it will be equal to plus 1, or it is equally possible that it will be equal to minus 1 or plus 1. So if you sum them up, the expected value of this error becomes actually equal to 0. So the expected value of the error is 0, which means the expected value of xt is equal to xt minus 1. Now, if you want AR model has to be covariance stationary. Now, the first condition of a covariance stationary model is fulfilled. If you take xt plus 1, the best guess will be xt, whose best guess is xt minus 1. So all these values, all the x values are basically constant. So all the expected x values are basically equal to a constant. So the first condition of covariance stationary is fulfilled. Now let us look at the second condition. What is the variance, friends? Let's say x1 is equal to 0. Therefore x2 is equal to error of the equation x2. Now this implies that the variance of x2 is equal to variance of error 2. This is equal to sigma square. x3 is equal to x2 plus error for a random walk, right? This is equal to nothing but error 2 plus error 3. Now variance of x3 is equal to variance of error 2 plus variance of error 3, both of which are equal to sigma square. Therefore this is equal to 2 into sigma square. Similarly, if you extend it, this becomes variance of xt is equal to t minus 1 multiplied by sigma square. This means the variance has no upper bound. Variance has no upper bound. It moves up as the t moves up, right? So this violates the covariance stationary condition. This violates the covariance stationary condition, right? Now, let us also have a look at the covariance. Let's say we are looking at the covariance at a lag of s. So covariance of error at t and error at t minus s. This is equal to expected value of error at t minus estimated value of error, which is 0, multiplied by error t minus s minus 0. Now the expected value of error t and expected value of error t minus s both are equal to 0. Therefore the covariance also becomes equal to 0. So these two conditions, covariance and expected value of xt, these two conditions are sort of fulfilled. So because one of the three conditions of being covariance stationary is being violated, the model is not following the covariance stationary rule. So how can we mitigate this problem, friends? Let's have a look at it. To make this model covariance stationary, what we do is something called first differencing. So we take out something called yt, which is equal to xt minus 1. This is nothing but xt minus 1 plus error minus xt minus 1, which is equal to nothing but error. So this is what the first differentiation looks like. Now this makes it covariance stationary. How so? First, the variance was violating in the previous equation, right? So let us check the variance here. Variance of yt, this is equal to variance of xt minus variance of xt minus 1. So this is equal to, from the previous equation, this will be t minus 1 into sigma square minus t minus 2 into sigma square, right? If you just simplify this, this becomes equal to sigma square. So the t variable is gone. Sigma square becomes a constant value, which is the variance of yt. So the variance part is gone. And the expected value of yt, is nothing but 0, because expected value of error is nothing but 0. Now this is one factor for the model to be covariance stationary. We have checked this is okay. This was being violated previously. The second factor, here also we are okay. The third factor, the covariance. The covariance of, let's say, error t minus 1, error t minus s. This is equal to nothing but 0. We have spoken in the previous formula itself. It is given by expected value of error t minus 0 multiplied by error t minus s minus 0. So if these are all estimated values, et and et minus s are expected to be 0. So the entire value is equal to 0. So the covariance is 0. So all the three conditions are satisfied. This is finite and constant covariance. The variance is finite and constant, and the expected value of the variable is also finite and constant. One more thing, if you want to confirm the covariance stationarity, is the mean reversion point. So the mean reversion point for the non-first differentiated model looks something like this. xt is equal to b0 by 1 minus b1, right? Here b1 is equal to 1 and b0 is equal to 0. So this entire value becomes 0 by 0, which is undefined. So the mean reversion point before first differencing is undefined. And what about yt? What about the mean reversion point after first differencing? yt is equal to, again if you write b0, 1 minus b1, here b0 is equal to 0 and b1 also is equal to 0 because we have seen here. So if you see the equation above, friends, here yt is equal to error t. So there is no b1 present, b1 is actually equal to 0. So here we can write yt is equal to 0 by 1 minus 0. This is equal to 0 by 1, or the value is 0. The mean reversion point predictably is 0 for a random walk. So we have a defined point of mean reversion. So this is another way which proves that yt is covariance stationary. So friends, what is a random walk with a drift? So we have learned that random walk is represented like this: xt is equal to xt minus 1 plus error at t, right? Now here b1 is equal to 1 and b0 is equal to 0. Now if there has to be a drift, what has to change here? The thing that changes is the b0. The b0 becomes not equal to 0. So this equation transforms to xt is equal to b0 plus xt minus 1 plus the error. This is a random walk with a drift. Dickey-Fuller unit root test. This is a test of what factor, friends? It is a test of non-stationarity. Now what do we mean by this? So friends, the random walk equation we can write like this: xt is equal to xt minus 1 plus the error, which is unpredictable, right? Now this is a special case of AR model, that is the autoregressive model, which is given by xt is equal to b0 plus b1 xt minus 1 plus the error. This is just a special case of autoregressive model or AR1 model. Now this model, AR1 model, has some limitations, friend. We cannot accept a model which has a b1 which is equal to or greater than 1. b1 cannot be equal to 1 or greater than 1. We only accept equations where b1 is less than 1. This is the only case where the non-stationarity condition is fulfilled. Now how do we test for it, friends? Previously we have tested autocorrelation by the help of t statistics, right? We have measured the t critical values. We have measured the t critical values and compared it with the t stat to find out whether the value is significantly different for 0 or not, right? We have done this error autocorrelation thing. You can find in the previous section. But here, friends, this is not possible. The reason being, at b1 equal to 1, the equation becomes non-stationary. The equation itself becomes non-stationary. So autocorrelation measurements with the help of t statistics cannot be done here, right? So we have to do something else. What do we do? Here we use something called the Dickey-Fuller unit root test. What Dickey and Fuller did is they subtracted xt minus 1 from both the sides. So xt minus 1 is equal to b0 plus b1 minus 1 into xt minus 1, because we subtract xt minus 1 from both sides, this happens, plus the error term, right? Let's just transform the equation a little bit. Now we call this yt is equal to b0 plus b1 minus 1, we call this g, multiplied by xt minus 1 plus error. Now we test for this g. That is, the null hypothesis says that g is equal to 0. That is, b1 is equal to 1, which implies there is non-stationarity. Non-stationarity is there. And the alternative hypothesis naturally is g is less than 1, which means non-stationarity is not there. That is, the model is valid. Now, how do we test whether the G is equal to 0 or not? Obviously, there is something called t-statistic for Dickey-Fuller test. And the critical value of this is greater than the absolute values of the t-critical values in normal t-stats tests. Right? So, the absolute values are greater. So, we measure the t-statistic with respect to G and compare it with the Dickey-Fuller t-stat critical values, and then if the critical value is greater, then we say the null hypothesis is rejected. So H0 is rejected if t-stat for Dickey-Fuller test is less than the t-critical for Dickey-Fuller test. So this is how the Dickey-Fuller unit root test is done for non-stationary difference. And this is obviously with respect to AR models, specifically AR1 models.